Hello everyone. For today's tutorial video, I'd like to explain how centripetal force and centripetal acceleration works, complete with demonstrations. As we can recall from studying Newton's first law of motion, an object will want to travel in a straight line path with a constant velocity if there are no forces acting on it. This may naturally lead you to wonder, how would rotational motion work if we know that objects want to naturally move in a straight line path? The answer to that is a special type of force called centripetal force. As we should remember that velocity is direction sensitive while speed is not. And we should also pay attention to the fact that when an object rotates in a circular path, the direction is always changing, even if the speed may be constant. This means, owing to the fact that the velocity is changing constantly, and remembering that acceleration is a change in velocity, that the object would have to be accelerating constantly by this definition. In fact, it was the genius of Sir Isaac Newton himself who discovered the exact mathematical definition of the force that would keep an object rotating, and gave it the name centripetal force, owing to the fact that it is directed toward the center. And like a lot of his texts during that time, centripetal comes directly from Latin, where the prefix centra means center, and the suffix petal may be a little more hard to distinguish because it is not standard to English, but comes straight from Latin, where pedal is derived from pater, meaning to seek. So therefore, a centripetal force is literally center seeking. Although this may seem incredibly hard, in fact impossible to believe from our day-to-day experience, it was Newton himself who first proved this in a strict mathematical fashion. His first step was to realize that the velocity was different at 2 points, as it is different along every point in a rotation, and then graph out these velocities using what is known as a vector, which is simply a number that has both a magnitude, i.e. a quantity, and a specific direction. And then he subtracted these two vectors and made the resultant vector a new one on his graph. And then he noticed that the direction of the radius at those 2 points was different, just like the direction of the velocities. He knew he could represent the difference between these radiuses the same way he represented the difference in velocities with a third vector. He noticed, geometrically speaking, that the difference radius was parallel to an arc length, or a slice of the circle's circumference. The next step he did was to compare these two triangles, and notice that they were both isosceles, i.e. that they both had two sides that were identical, because of the fact that the magnitude or speed of the velocity is constant throughout the rotation. He then knew, because they were both isosceles triangles, that they were identical in terms of shape. The only thing that was different about them was the exact length or proportions of their sides. So he wrote this mathematically as the difference in arc length divided by the radius equals the difference in velocity divided by the individual velocities, as this is the ratios that matches the corresponding sides of the isosceles triangles. He then remembered, by the exact definition of acceleration being change in velocity over change in time, that he could isolate change in velocity by itself by multiplying both sides by velocity. And we get change in velocity equals velocity divided by radius times change in arc length. Finally, he got it in terms of acceleration by dividing both sides by change in time, so we get change in velocity over change in time equals velocity divided by radius times change in arc length over change in time. And that is the linear velocity along the arc called the tangential velocity. The final step in his proof was multiplying v divided by r times this newly substituted in v, which is v squared over r. So our final answer is centripetal acceleration equals v squared divided by r. Although this may seem useful only in theory, it actually has very real consequences in our physical world. For example, if you have ever driven a car or rode a bicycle, you will notice you will feel a sharper sideways acceleration if you have a sharper turn, or if you have a greater turning speed. We can next derive centripetal force in a more simple manner by remembering that force equals mass times acceleration, and so therefore centripetal force must equal mass times centripetal acceleration, or mv squared all over r. Since we know that forces alter an object's motion, it would stand to reason, mathematically speaking, that a centripetal force must be greater than other forces in order for the object to rotate. As you can see for yourself if you ever swing a bucket of water over your head, or if you ever paid close attention to the loop-de-loops on roller coaster rides. This also means that a more massive object will be harder to accelerate centripetally, just like it is harder to accelerate in terms of linear motion. This also means, exactly like how linear motion works, that an object that is more massive and undergoes centripetal motion will be harder to stop rotating than a less massive one. With all the descriptions of constant speed rotational motion described in detail, we can move on to accelerated rotational motion in the next tutorial video. And also, we will discuss how torques work, which are forces that cause objects to rotate faster or slower, just like how forces cause objects to move faster or slower in terms of straight line motion.